Okay, so today we're going to talk about probability mass functions or probability functions, whatever you want to call it. Doesn't really matter. That's a good enough name. Oh, it's slow. So one of the things you can do, and we do this with, you think about Z tables, T tables, those kind of things. We do this all the time. You can plot the probability of any given score for a variable. That's in fact, when you look at a Z table, which you all looked at in intro stats, you can plot the probability of any score for a variable, any variable. And the probability of all of the events, of all possible scores then, or all the events, if you want to use a technical probability term, is 1. So if I add up the probability of every possible event, I get 1. Does that make sense? Because probability of 1 is definitely going to happen. Okay, does that make sense so far? Good. So that means then, the area under that curve is 1. Okay? Does that follow? Does that make sense to everybody? So the area under the curve then is 1. Because you're plotting probability, the probability of all possible effects has got to be 1. So the area under the curve, therefore, is 1. Okay? All right. Let's say you were rolling a die. Those really shouldn't be solid bars, they should just be lines, but that doesn't matter. The probability of getting a 1 is the same as a 2, is the same as a 3, is the same as a 4, 5, and a 6. That's if you're using a 6-sided die and not one of those 20-sided Dungeons and Dragons dies. Right? So the probability of each possible roll is 1. Or it's 0.1, that's right, it's 1/6, because there are 6 possible outcomes, and they are equally likely. And 1/6 times 6 is 1. So the area under curve, we had a curve drawn, will be 1. Okay. So you're all with me so far? Yes? Okay. So let's think about the normal distribution. That's the old Z distribution, or if you're American, the Z distribution. I like Z better. It sounds better. Look at that. There's 1. It's got some interesting properties. You know, we're going to have so many standard deviations from the mean. That's 1 standard deviation from the mean. This is 2, etc. That's a standard normal distribution. It's got a mean of 0 and a standard deviation of 1. We use this a lot, right? And it's the most common, or at least for us, the most useful distribution. In fact, all the statistics we talk about, all inferential statistics that we're talking about, parametric inferential statistics, are based somehow on the normal distribution. They're somehow based on the normal distribution. Okay? Has some characteristics that are interesting, as I mentioned. It's unimodal. Means it's got 1 mode. It's symmetrical, so it's not skewed in any way. It's completely symmetrical. And it's bell-shaped. If we want to describe the shape, we'd say it's bell-shaped. Sometimes called the bell curve, even. Right? So unimodal, bell-shaped, symmetrical. Question so far? I was saying to Paul before that I got to stop saying, and you should know this because you learned at 2126, because it makes people feel like they shouldn't ask questions. Even if I say you've seen this before, please, if you don't follow something, ask, okay? Because I want you to ask questions. Okay, so you're good so far? Yeah? Excellent. You might ask yourself, how did I get here? That's from a Talking Head song, which is before all your times. You might ask yourself, why is this useful to know that? Well, many variables are assumed to be normal in the population. Note the word assumed. Actually, a lot of variables actually aren't normal. There's a lot of examples you get in intro stats books. They're great. And they say things like, the life of a light bulb is normally distributed with a mean of this many hours. No, there's no damn way a life of a light bulb is normally distributed. You had to be a shitty light bulb company if you had as many that lasted really long as lasted really short. Right? You don't want to put a light bulb in and it explodes. There's no way that's actually normal. We assume things are normal. Some things really are. Human height of adults is almost certainly normally distributed. Right? And when you do adult male versus female, probably in that case. But it's somewhat, weight is probably normally distributed, pretty much. So some things are. Some things are designed to be normally distributed. IQ tests are normally distributed, but they're designed that way. They're built up. Makes the stats easy. So a lot of things are assumed to be normal in the population, or actually, sometimes actually are. So we can use some standard techniques if everything's the same. See, because the numbers don't know where they come from. And because the numbers don't know where they come from, we can do the same thing on things about heights as we do on things, let's say, IQ scores. Now, sampling distributions are normal. What's a sampling distribution? Sampling distribution is when, let's say the mean. Let's say a mean of 10. A mean of 10, like n is 10. 10 observations. And you are randomly drawing 10 scores from the pool of whatever the population is. If you were to plot the mean that you get each time, if you were to plot the mean you get each time, you actually end up with a normal distribution. What? How is that true? Well, it's because of something called the central limit theorem. You can actually prove it to yourself. It's kind of fun if you've got a little bit of time on your hands, and I know students have so much time on their hands. Take a coin and flip it 10 times. And assign a value of 1 to heads and 0 to tails. Do it 10 times, write down the number you got. Then do it again, write down just do this 30 times. And plot it. And sometimes you'll get very few heads, and sometimes you'll get lots of heads. More likely you get a few, and a few, more. But most times you're going to get 5 and 5. And you plot it up, and it'll look like this. It's really cool. And that's with a distribution that has 2 possible scores in the population. But the sampling distribution will be normally distributed. So that's because of a thing called the central limit theorem. We won't get into a proof of the central limit theorem. That's well beyond the scope of this course. If you want to know the proof, all the way back to my office, I'll dust off one of my old graduate student textbooks and I'll show you the proof. Or you could just believe me. Or you can try this, or do a roll of die. What's your average roll of, say, even 5 rolls, and do it 20 times. And plot it up. You'll get a normal, you get something approaching a normal distribution. It's very cool. So sampling distributions are actually normal. In fact, that's the most useful thing for us. Because we're always going to be using samples, not populations. Questions so far? Do you have any questions? Okay. Wait, what's that mean? The sampling distribution of the mean, this is just some notation, okay, is normal with a mean of mu and a standard deviation of sigma divided by the square root of n. So the sampling distribution of the mean, what you're doing in this case is you're actually taking the average. And it sounds weird to do that, except the numbers don't know where they come from. So it's the average is going to be normally distributed with a mean of mu sub x. In other words, it's going to have the same mean as the population mean. But the variance, sorry, I keep saying variance, the standard deviation is going to be sigma, the population standard deviation, divided by the square root of n. Now, we don't know sigma usually. You know, it's hard to even know, a lot of times to know mu, the population parameter for mean, but we can usually guess it. We can intuit it. It's hard to know what it is, what the standard deviation is. But think about this. What happens to the quantity what's the limit as n approaches infinity of sigma divided by the square root of n? What that means is, actually, is anybody here have you done limits in math? Jeez, very few of you. Okay. All that's doing is figure out what happens as n gets really, really, really big. What happens is that n gets infinitely large. What's going to happen to that quantity? Sigma over root n. What's it going to get to be? If you're taking a fraction, sigma's not changing, but you're dividing it by 10, what happens if instead you divide it by 100? It gets smaller. What happens as it gets infinitely large? What does it become close to? 0. Yes. So the limit as n approaches infinity of sigma divided by the square root of n is 0. So that's one thing if you've done limits, which apparently none of you have, or one of you has. On the other hand, just think about this rationally. If we took the average height of all people in the world, there's 7.5 billion people. Let's go with that number right now. A little higher probably. Let's say 7.5 billion. Let's assume none of the people die between our sampling, which we're making some tenuous assumptions here. But anyway. Okay, let's not make all the people in the world dead, because I think it gets kind of weird. All students at Sault Ste. Marie campus at Algoma University, we can do that. And we're going to measure their heights. And we're going to take the mean, and we're going to plot it up. And then the next day, we're going to do the same thing. And then we're going to do the same thing. You know, we're going to get the same damn score every time for that mean, right? Because we're sampling the same people, all of them. So that means, and what's the variance of a score that doesn't change? It's 0. Right? Because if I keep measuring, writing down the same number, I get a mean of whatever, let's say it's 170 centimeters. And I calculate the standard deviation. I go, let's just use it 170 minus 170 squared plus 170 minus 170 squared plus 0 plus 0 plus 0 plus 0 plus 0. It's 0. You're measuring the whole population. If your sample becomes your population, your variance is nothing. Does that make some sense? Dark here, so I can tell the looks on your faces, but okay. I'm going to assume you all understood that perfectly. So, some properties of distributions in general. So we'll leave the normal distribution for a second. Step away, and we're going to go to this weird triangle distribution that I invented and have never seen in the wild. The probability of getting a value between 3 and 7, which I believe is the Queens of the Stone Age song. 3 and 7, nobody? Nothing? Nobody? Okay. Anyway, is the area between f at 3 and f at 7. It's this area here, that house-shaped thing. Okay. How are we going to calculate that? Well, it's the area under that curve. Well, in that case, we can actually use geometry. We could do a square. I don't know what the formula is for the shape of a house like that is, but I know what the formula is for getting the area of a square or rectangle, or the area of a rectangle, or sorry, a triangle. I can do that. I learned that in grade 6 or 5 or something. 4 or 5. Okay. So simple geometry, you can do it. Define the area under the curve. That'll tell you the school, probability of the score between 3 and 7. It's not a common shape. I asked you already, I think maybe 2 of you have taken calculus in class. Calculus is about 2 things. It's about slopes of curves at certain places, and area under curves. Oh, area under a curve, eh? I see, that might be interesting and useful to us. Right? Could be useful. So if I knew what the equation was for that weird triangle shaped thing, so that's f of x, and I calculated the integral of that thing, this is calculus. If you don't know it, don't worry, I'm not going to ask you, I'm not going to teach you calculus. It's not going to happen. Okay? You got a chance to do that in your life. That chance is passed for most of you. And it's a value between 3 and 7 of this. And if you have taken calculus, you look at that and go, yeah, I guess depending on what f of x is, I could probably do that pretty easily. And many of you are thinking to yourself, but I don't know how to do calculus, I'm frightened. Don't worry, you don't have to know how to do calculus. Well, it is your loss. It's too bad you don't know how to do calculus, because it's the most beautiful math there is, to me anyway. It's beautiful because it describes the universe. It's this math that describes how everything works. It's really cool. And if you're into biology at all, like behavioral ecology, that kind of stuff, and those of you who took behavior with me last term know that I would often say, now if you're into calculus, so there's a lot of, when you do advanced things and things like behavioral ecology or behavior, where you do some things about perception, some advanced things like neuroscience, calculus becomes really useful. It's not just in physics and engineering and chemistry, it's in like life sciences a lot too. So if you do go to graduate school and are interested in those kind of topics, at some point you're going to have to give yourself a little crash course in calculus, which is not that hard actually. And once you get calculus, you go, oh, that's cool. It really is too. So, while it's too bad to be you because you know calculus, somebody did some calculus for us, which is really nice. So here's the formula of the normal distribution. That's really helpful. So f of x or y equals, if you think back to high school math, it's 1 over the sigma times the square root of 2 pi times e to the negative x minus u divided by 2 times the variance squared. 2 times the variance, I'm sorry. Okay? E is just a mathematical constant. You know pi is probably, but e is another mathematical constant. It comes up a lot. It's the base of the natural logarithm. It's like 2.71828. And pi is 3.1415927. Basically, that much. If you have that much precision, you're fine. You don't really need any more precision than that. There's probably, if you got an advanced calculator app on your phone, it's funny, if you have iOS, you look at it straight on and it looks nothing special. You turn it sideways, suddenly on the side of the calculator, there's an E button and a pi button. I've probably dealt with E and pi before. Definitely dealt with pi before because they teach you how to do circles and that in high school. You might have dealt with E as well. But this is actually, there's a formula of the normal distribution of that bell curve. Those of you who have taken calculus look at that and go, that's an ugly thing to take the integral of. It's a hard integral. So, you just take the integral of this function. Which it's almost impossible. That's a very hard one to do. So let's say you want to get but let's just pretend. Let's pretend. Let's take a flight of fancy and live on Lollipop Lane. And where we ride unicorns and do calculus. Let's say we want to find the probability of having an IQ between 95 and 107. Just take the integral of this and put 95 and 107. Yay! It's easy. It's easy theoretically. Theoretically easy. You can actually make it a little bit easier. Make it a lot easier. What if you make the mean 0 and the variance 1, which is called the standard normal distribution or Z distribution, right? The equation is a little bit more simple. I know that's still complicated, but it's a lot simpler than what we had. Because now everything with the variance is just 1, and everything with the mean is 0. So now this is the function of the standard normal distribution. Okay. So f of x equals 1 over root of 2 pi times e to the negative x divided by 10. So it's easier. It's not super easy. But if we convert everything, all our distributions, whenever we have something that's normal, and we convert it to a mean of 0 to variance of 1, we can now use this standard thing. Someone has actually done this calculus already for you and found out how likely it is that certain scores fall between certain areas underneath the curve. Some poor set of graduate students a long time ago churned these tables out. So you see those Z tables in the back of your stats book? That basically they're all just solutions to integrals of between here and here, and between here and here, here and here. That's all that is. So every time you look something up in a table, in a stats book, I want you to say to yourself, thank you, unnamed graduate student from 18 whatever, for taking your whole career just doing integrals all damn day, you boring, boring jerk. Thank you. Probably not a jerk. Probably not boring, probably a very interesting person, but their job was boring. Say a silent little prayer to those people from back then. Someone did the calculus for you, so you don't have to. So you don't have to. So this is in fact what we do when we use our standard distribution with standardized data, we make it between 0 and 1. So you take a score of some sort, and you convert it into a Z score. Then you look it up on a table, and you convert the other score to another Z score, and you look between those two points, you find what those probabilities are, you go from there. Now, so 95 is negative 0.32, 107 is 0.466. The probability, I'm not going to go through all the extra arithmetic I did here. I looked it up in a Z table. In fact, I actually used my own calculator. I used to have a really good calculator. It wasn't expensive or anything, but it had a Z function built in, so I could look up probabilities of Z scores. So I looked up the probability of getting between negative 0.32 and 0, and a probability of 0 and 0.466. I added them together, those two probabilities, and it's 0.31. So there's a 31% chance of getting having an IQ between 95 and 107. Right? And I know that you may have forgotten a lot of this stuff, but you have done it. They were horrible, boring homework assignments, and you did hundreds and hundreds. You did lots of questions. What's the probability of getting a score between this and this? And you always wondered, does anybody do this in real life? And the answer is yeah, in stats class. No one really wants to know what the probability of getting an IQ between 95 and 107 is. But you know why we use IQ all the time? Because we know the standard deviation. It's 15. Why is it 15? Because the tests are built that way. It's built at a mean of 100 and a standard deviation of 15. It literally, those tests are built that way. So all you're doing, we standardize our data using the Z distribution and make it normal with a mean of 0 and a variance of 1. When we do that, we can then use the standard table, and hey, lo and behold, some poor bugger's done the calculus for us. So we don't have to know how to do calculus. But there's always the calculus that's behind this stuff, which is what makes it cool. Do you have any questions so far? What are your questions for? Somebody have a question? Does anybody have a question? You guys have a question? We have a question. You get it? You have a question? You have a question?
I was just thinking about complicated formulas.
What, the complicated formula?
Yeah, I just wanted to make sure that the
Oh,
score was.
Oh, right.
Okay.
Yeah, z-score is just, x minus mu or
Yeah.
sigma. That's right. And any z-score, if you remember learning about all these statistical tests, learning about z-tests, and then eventually t-tests, which we do next time, you thought, oh, that's some kind of magic thing, and all these formulae are different. They're not. They're actually all based on this. It's all based on this. It can get more complicated if we're using a sampling distribution. It's going to be x bar. It's going to be divided by sigma divided by the square root of n, because that's the standard deviation for a sampling distribution. But they're all the same thing. And I know you're typically taught, and there's nothing wrong with this, I was taught it this way too, that they're all different. They're actually not. They're actually not. They're all exactly the same damn thing. I don't know, maybe Dwayne teaches it like they're all the same thing, which more power to him if he does, but most people don't, and that's fine, because it would make most people's heads explode in interest class. Yep.
So you get the 0.31 by looking at like a score chart?
Yeah.
Okay.
I looked at, and what I looked at, or I used my calculator, but what I looked at was the probability, and you could do this yourself. So if you look at the back of the book, drawing pictures can be really useful. So there's 0, it's got a variance of 1. So between negative 0.32, which is going to be about there, and positive, what's the positive value? 0.466. So it's that area between here and here. Now, typically a Z table is not going to actually tell you those between those two things. Why would it do that? But it'll tell you between 0 and that value. So you look up for negative 0.32 and add that to positive 0.466. You'll add those together, and that'll give you 0.31. So you look up the probabilities from the Z table of those two numbers. That's how you do this kind of question. Okay? And again, typically, this isn't something we do in the real world. This is the reason we teach in this, especially in an intro stats class, and spend a week and a half doing things on z-scores, is because it's the basis for everything. You have to understand that first. But no one sits around calculating z-scores. It's not a thing. I mean, probably somebody does, because there's got to be some 7.5 million people who wrote some freak who really likes z-scores. But typically, people aren't into that scene. So someone did the calculus for you. So you can just look this stuff up now in a table. There's also a nice web tool here. Now, does that link work? I think it does. But if you look at the link here and mess around with that, you can see that it's really easy to use. That will allow you to just put the scores in, and it just does it magically for you. It's wonderful. Assuming that website's still up, it was last time I checked, which was last year. It still works? Excellent. So if you take a look at that, and here's in fact what it looks like when you do this, you would put in between, this is the beautiful thing about this is, unlike a Z table where you're not going to find, oh, what is it for between negative 0.32 and positive 0.466? Because a Z table won't do that, but this can. So you can actually do it between. The other way you would do it is, as I said, the way we would do it with a Z table is you go between here and here, between here and here. But the beautiful is, and look, 0.304, and I said 0.31, right? 3049, which rounds up to 305, which rounds up to 0.31. So my calculator was right. My calculator that I bought on my first day of graduate school, that my son managed to wreck. Doesn't really matter. calculator app on my phone is way more powerful than that calculator. Also, the calculator was bought for me by my guy who was my TA in my stats class for graduate school, for stats class. And I was standing in line, I had my calculator, and I didn't have enough money to turn it in my pocket. This is before bank cards. And this guy in front of, beside me says, "Oh, are you in Psych 2001?" Which was, we used to call it Psych 2001 Stats, obviously. He said, "Yeah," he said, "I'm the TA, so I'll just need like $20 for the calculator, just bring it to the first class." And I paid him back. And then 2 years ago, he got fired for sexual harassment at his job. So it turned out the guy I knew was a really horrible person. I didn't know that. That's awful. So he didn't get fired. He retired early. Ew. People are awful. They're pigs. Jeez. It's horrible. Anyway, hashtag no women. So, I'm tired of that, by the way. When people say that, they don't mean you, they mean, I'm a middle-aged white man. The world's set up for me, and it enrages me. Anyway, enough of that. So it's good the calculator's going because it reminds me of this horrible person who I thought was a good guy. It's really annoying. When I read about this thing, oh, is it him? Because I knew at university said, don't be a click. Oh, it is. He was the only person at that university who I knew. So I thought, please don't be. All right, that's horrible. Boy, to get done quickly. Okay. We can conclude this very early. You're not asking enough questions. We can conclude by saying you're not asking enough questions. Some poor person did the calculus for you. So you are able to do these things without worrying about having to do calculus. But you should keep in mind, like I said, seriously, the first nice thing is there's a beauty to this stuff, and that's that calculus can actually describe the universe, is a neat thing. But also, just think back to the poor bugger who did that work for you. It's nice. We now just look things up on a table, or like the web tool I showed you. It's very useful. So let's say on the test, would I do something? I'm not going to, no, I wouldn't give you that question. But if I did, you could just use that web tool. Or you could use the set table in your book. But I can tell you there's not a question like that on the test. I don't know. You've been tested on that already in another course. And if you're in this class, I'm going to assume that you know how to do that. Even if you've forgotten how to do it. That you look back today and go, oh, I see that thing there. See, this isn't scary. You already knew how to do this. But one of the things about statistics is that, especially at sort of the introductory level, you're not told why it works. You're told that it works and to trust it on faith. Right? So it's like you're Catholic and he's Pope Dwayne Keogh. I think there's been a Pope Dwayne. Dressed up as the Pope at the Halloween party. Just saying. You really did. So now you know why it works. And the crux of this course, frankly, is why stuff works, not just that it works. Because if you know why it works, you understand the basis of statistics, you can then figure out any kind of statistical problem, because you understand the mechanics of it. Do you have any other questions for me? You sure you have no questions? All right, you have no questions. So then we will